the ductility coefficient R is 8.5. So you can find the R or the ductility coefficient on table 208-11A. So we will be using special reinforced concrete moment frames. So for the distance from the known source, if not stated in the geotechnical report, we may use the fault finder of FIVOLX. You may search it on Google or use the link faultfinder.fivolx.dost.gov.ph. So for this example, we are assuming that this school building is located somewhere 10 kilometers away from a known seismic source. So for the CACV, the program will automatically compute this based on the distance from source and source type that we entered. But if you want to verify, here's how we can manually compute for the NV and the NA, or the CA and the CV. So for NV and NA, we may choose the values in these tables presented on the screen. So I got these tables, by the way, from NSCP 2015 Chapter 208. So the code also allows the interpolation of the values here. So now let us confirm the input in midas engine. So since NSCP is referenced from UBC 1997, so we will use UBC 1997. Soil type SD, CACV, this one is auto-calculated by the program based on the seismic zone that we input. So that is the seismic zone 4, seismic source A. Closest distance known to seismic, that is 10. Importance factor 1.5. So the period also is auto-calculated by the program. So you will just choose this number 2 since this is for the concrete. Calculate. And then for the ductility coefficient R, we use 8.5 again because we are using an SMRF frame. So if you want to verify the input, you can click report, and then also a Word format will appear. And then it will present you all of the input and the calculations of the base shear. So after the verification of the geometry and the loadings, we now go to the analysis. So this is our next phase of the discussion. So in Engine, we have three ways to check the result of the model. So to roughly evaluate, we can do the visual checking. For detailed checking, we can do the tabular format. And for the final checking and for submission purposes, we can produce the reports in Word format. So let us start the discussion by roughly evaluating the model. To check for the analysis results, we first have to run the model. So check if you have a post node, so here, or Ctrl plus F8. After running the analysis, we will first check the model behavior under gravity loads. So this is one way of checking if there's something off in the model. I will first discuss the components that we are about to see on the screen. We have the works tree as discussed earlier, but now we have the analysis results works tree here. So this once we have run the analysis results or the design results works tree will appear in works tree. So we have the message window. So we can see here all the messages such as the errors or if the model has been auto-saved and the likes. So of course, the model area now that is in color coding, we have the legend here on the right side. The legend shows us how many percent of the model is failing this much or how many percent of the model has this ratio. So since we are checking for the deformation, let us go to the status bar and choose millimeters. So the deformation will be shown here on the right side of the legend. So it only means that 0.2% of the model is deflecting by 8.7. So aside from the color coding, to visualize better, we can check the form so we can see its actual behavior. So checking the behavior of the model under gravity loads will also help us see if there are unconnected nodes, since under dead load alone, we know already how the model should react. Okay, so next we will be checking for the settings. So again, let me repeat that all of these inputs are based on the designer's preferences. And for this discussion, I will be using these values, of course, in conformance to NSCP 2015. Since we are checking for deflection, we shall first review the values set by the program. So for the limits, according to NSCP 2015 table 424.2.2, so for roof or floors not likely to be damaged by large deflections, we can set the limit to L over 240. So here in the design settings, we input 240. Live load sustained ratio, I used zero point 0.2, and for the time dependent factor, got it from table 424.2.4.1.3. So time dependent factor for sustained loads for 60 or more months, we have 2. So I set this limit to 2. And now we're in serviceability checking. Let us also see the design settings for footing. So under the safety factor, I am using the usual values, 1 for compression, 1.5 for sliding, 1.5 for uplift, and 2 for overturning. So these inputs are also editable, so you may change it according to your preference or according to the geotech engineer's reports. And before we check for another behavior of the model, we must also first confirm the generated load combination. So in midas engine, we may auto-generate the load combinations or we can manually input them. So for the auto-generation, we have ACI as a database for concrete load combinations. So this one ACI. Since ACI is the reference of NSCP, we will be using this. So anyway, if you have changes or if you prefer to manually input your load combinations, we can use the copy and paste command from your Excel files. So for easier verification, we can copy the actual combination description to the name. So this is the description and this is the name. So what I did is I copied the description to the name. So when I am checking, I can easily check which combinations go good. So let's go to the results and design results. So let's check for the serviceability. So let's look for the bearing capacity of the footing. So this time, the legend shows us the ratio. So if none is beyond 1 or none is more than 1, so therefore our model is safe in bearing capacity ratio check. So for the overturning, we can see also that we have 0.13 for the maximum ratio. And for the sliding ratio, we have 0.87. So for the footing, this one is the most stressed member because it has the largest ratio for the bearing capacity, for the overturning, and for the sliding. So that's how you can roughly evaluate using visual checking. Okay, so now let us interpret the results and design. So again, let us first verify the designer's input under the design settings. So we go to the design and design settings. Okay, so for the code category, as mentioned earlier, NSCP is patterned or referenced from AISC and ACI. So we are using AISC, ASD for still, and ACI for RC. So next, we may edit the checking controls. So we go to the checking controls and we can edit the result criteria here. So let me clarify again that it is your own discretion. So if you are open to consider demand capacity ratios over 1, so you can do so. I am only showing this to you so you know where to edit them. For the criteria of check status, so you can choose which color you want to represent the not good, the failure, or the okay, or the need check. Okay. So for the still, since we have a truss in this model, so let's also edit the parameters in still. So this one, so we have a lot of parameters to consider in still design. So you may confirm it here in NSCP 2015 chapter 504 to 507. So for the tensile yielding, we have safety factor 1.67 for ASD since we are using the ASD code of AISC. So for tensile rupture, we have 2. For the design of compression, for compressive strength, we have 1.67. For flexure, 1.67. And for shear, 1.67. So for the slenderness ratio, it says here that it shall not exceed 200 for members designed for compression and 300 for members designed for tension. So we put here 200 and 300. So this one. Of course, there is an exemption. So the rods and the hangers and tensions are exempted in the L over R ratio. So how do you exempt them from the checking? So this one is the default setting. So those checking controls I showed earlier were the default settings that are applicable to all members. So now if you want to edit a parameter per member, you may do so here. So this applies to what I have, to the exemptions as I have mentioned earlier. So for example, we have bracings that are still rods. So we can exempt them in the checking of the slenderness ratio under tension. So you can uncheck this considered under limiting slenderness ratio for still. So or if you want to add unbraced length, so you can uncheck the program determined and then you put values in LY and LZ. So now that we have checked all of the design settings, checking controls under this tab, so now we can check for the design results. So in design results, we have the total status again. So under strength check, so earlier what I showed you was the serviceability check. Now we are checking for the strength. So in visual checking of the total status, you can see right away the failing members. So these members are in color coding. So for the red, those are the not good or the failing members. So the result criteria for the not good, for the failure, for the critical, so we edited them earlier. So I showed you that earlier in the design settings. So you may check if it fails or if it is more critical under strength or under serviceability. And the other checking criteria that are written here. So you can check for the axial ratio for the columns. And then again, right away, you can see the failing ones. And then it will show you the ratio. So mostly are here in the green, which are 0.73 and 1.17. So that's just the downside of the visual checking. So that's why I call it the rough evaluation, because you cannot really pinpoint the exact ratio of a certain member. So to do that, you have to check in the tabular format, which I will be discussing later. So we go to the model works tree, and then when we hover our mouse to the A36 material, so since the truss members are the only still members in the model, so only those in A36 materials will be highlighted. So you right click and then show only. So now you can save this view by clicking the wheel button of your mouse. And then you click this one. Okay, so you will see in the message window that you have saved a current view named view 5. So you can rename that. You go to the display works tree and then you find the view 5. And then you can rename it. So you rename it to trust view. So then every time you want to check your trust or every time you want to view your trust, you can just double click this view. So for example, okay. And then you go back again to the design results and then you check for the actual ratio, for the bending ratio, and even for the combined ratio. Okay, so that's it for the visual checking. Now let us proceed to the next phase. So we have the tabular format. So if we want to check the model in a more detailed way, or if we want to extract the forces and paste that to our Excel spreadsheets, so we can use the tabular format. So let's start again with the serviceability check. So using the tabular checking, we may check the model if it passes in different story checking. So again, all the parameters or inputs that we need to know will be presented here. So you go to the table works tree, story, and then you go to the parameters. So here in the parameters, we can input the amplification factor, which is 0.7 times R. So then after setting these parameters, we may now check for the tabular results. So we no longer need to manually compute if it passes for the drift. So the program will do that for us. We just have to set the